Okay, let's move on with our discussion of energy. The whole second semester is about energy, and now there's this really, really big part of it, which is talking about energy that moves in waves. There's a lot of energy types that transmit themselves through waves. And so we have to talk about the nature of waves in general first. So what we're going to talk about today applies to sound waves, water waves, light waves, waves on a rope. Anything that moves in a wave is going to be this stuff today is going to be true about it. So let's just define a wave first. A wave is simply a rhythmic disturbance, rhythmic being in a rhythm that carries energy from one place to another through matter or space. Now, there's a couple of things I want you to understand about this definition. First of all, a wave could just be a single pulse. So if you look at this picture on the top, there's simply a single wave pulse that's traveling through that medium, but the wave on the bottom is actually a different type of wave. But there are multiple pulses. You can see multiple waves traveling across from left to right in that one. So this one is more rhythmic. This one is not quite as much. But a wave, so this is one wave at the top. This is multiple waves at the bottom. Second thing we need to understand that's really, really important, like if you're writing notes right now, which you really should be, you have to write this. Waves transfer energy. Waves transfer energy, not matter. Waves do not transfer matter. They only transfer energy. And here's a great example of this. When you were a little kid, you find a puddle or you go to a pond. My kids do this. When we get to a pond, it's like there's this thing. They have to reach down and find a rock, and they need to throw the rock in the water, right? They try to skip the rock or they just throw it in. And when you throw it in, the ripples on the pond look like this. And it should be fairly obvious that it's not possible for the waves to remove water from the pond. You can't empty the pond, even though the waves are spreading from the point where that rock entered the water all the way to the outsides of the pond. They go outward. That's because of the second law of thermodynamics. Energy spreads out. But it's the energy that is spreading outward toward the outside of the pond. And that energy is not carrying matter, which in this case is the water. You cannot empty a pond by throwing a rock into the pond. You're not moving any of that water. It's just that the molecules of the water are being used to transport the energy from where that rock hit the water to the outside edges of the pond. And it's interesting when you look at that energy transfer, by the way, that energy was inside of you. And that energy through ATP and muscle contractions got transferred to kinetic energy of the rock, which gets transferred to some sound energy, a little bit of heat when you hit the water. And then that energy gets transferred to the energy of waves on the surface of the water, which eventually reach the outsides of the pond. Energy is all connected. We need to talk about wave types. Waves can be classified in probably a lot of different ways, but we're going to talk about two different ways to classify waves. We're going to classify them based on two things. First of all, we're going to classify them based on the direction the particles oscillate, like the particles moving back and forth. And that's like in these, if you watch these particles, the particles are the individual dots, they're moving. We're going to classify them based on how the particles oscillate and based on how, like as in what method the wave uses to propagate. Now, the word propagate, if you've never heard it before, you need to know it. We're going to talk about it a lot in this section. Propagate or propagation just means movement. The way that a wave moves or goes from one place to another is called wave propagation. So in terms of how the particles oscillate, we're going to talk about transverse waves and compression waves, two divisions of waves, two types of waves based on how the particles oscillate, like the directions the particles are moving. But then there's two other kinds of waves based on how the wave propagates, and those are called mechanical waves, and electromagnetic waves is the other kind. Mechanical waves and electromagnetic waves. All right, so let's go ahead and jump in here to types of waves. Let's first of all talk about the direction of particle oscillation, all right? So we're in that first category right here for right now. We're going to talk about transverse waves first. Definition of a transverse wave, that's a wave in which the particles move perpendicular to the direction in which the wave moves. Perpendicular means at a right angle, a 90-degree angle. So if you watch this picture down here, you'll notice that if you keep your eye on an individual particle, the particles themselves simply move up and down. So the vibration or oscillation means move back and forth movement. The vibration of the particles are up and down. But if you look at it as a whole, you can clearly see that the wave is moving from left to right across the screen. So the Vibrations are perpendicular to the actual direction of wave propagation. The wave itself is traveling from left to right. If we have repeated pulses on a transverse wave simply look like water waves, look like waves on the water. As a matter of fact, when we look at examples of transverse waves, water waves are one example of a transverse wave, at least surface water waves. But also radio waves, microwaves, infrared, visible light, UV, all of these things are examples of transverse waves. And let's look at some examples here just by picture. You might have seen a picture that looks like this on the internet. There's a lot of YouTube videos where they show, oh, look, you can see waves on a guitar. Well, you need to know when you look at this, this is not the waves on a guitar string. Now, there are waves, but that's not what this is. And just notice, by the way, these waves are incredibly irregular. Right? The distance between the waves is different. They look all funky. Y'all, this is not what a wave looks like. That's not what's going on here. This is actually just a byproduct of how cell phones take video and the frame rate that they use. And it's something called, I think it's like progressive frame or something like that. Anyway, that's not a wave. Guitar strings do make waves and they look like this. Now, if you look closely, you can see that transverse wave very clearly traveling up the string and then back down. Same thing with a violin. As the violin bow gets pulled across the string, you can see the transverse wave traveling down the string and back up and down, up and down. It's a propagation of energy by a wave, right? We can look at water waves. Water waves are very clearly examples of transverse waves. These waves are going up and down, up and down. You can see that. The wave, when you go to the baseball game, football game, whatever, you do the wave is a great example of a transverse wave because each individual person is a particle in the wave, and all you have to do the wave is go up and down. Up and down. But the wave travels, in this case, from right to left. That is perpendicular. If you go to the gym, you do these battle ropes, right? That's a great example of a transverse wave. Lots of examples of transverse waves. If you've been to SMU, you might have seen this sculpture, which is just simply a bunch of bars. Turn that down a little bit. You don't really need to hear it. That you can see they're simply seesawing back and forth, but they're doing it in a rhythm, one after another, and you can see clearly it makes a transverse wave pattern. The particles themselves are moving up and down, while the wave, if you look at it just as a whole, the wave itself is moving from left to right, right? So all of these great examples of what a transverse wave looks like. All right, I want you to pause the video if you need to. I need you to draw this in your notes first. Draw this wave. Make sure you have this zero line, the resting position, drawn right through the middle of the wave. Pause the video for a second if you need to do that. All right, let's go ahead and move on. We need to talk about different parts of transverse waves. You really need to know, and you need to label on that picture you just drew, the different parts of waves. The first thing is called a crest, simply the top of the wave, really, really easy. Second thing I need you to know is a trough. The trough is the bottom of a wave. Think about a feed trough, like where you imagine you could put food right there to catch the animal feed. Trough is what we call the bottom of a wave. This one is really important. You need to circle it. The wavelength. The wavelength is what it says. It's the length of a wave. A wave is the distance between successive parts of the wave or the same parts of the wave. We usually measure a wavelength from one crest to the next, or it could be from one trough to the next, or from this part of the wave to the next identical part of the wave. That's the length of the wave. That's one wave. And so you can see here, the wavelength, that's a really good way to illustrate it. As this wave is moving, you can see the length of the wave there. So that's wavelength. The next part of the wave, of a transverse wave that you need to know, is called amplitude, and it's represented by these arrows here. The amplitude is the distance from this 0 point, from the normal resting position, which is where the molecule or the particle would be resting before the wave comes through and disturbs everything. So if this is water, that would be the very still surface of the water level before there's any wave coming through. And once that wave comes through, then that water molecule is going to go up and down. Well, the amplitude is how far that water molecule moves up past the 0 point and then also down past the 0 point. Okay, so make sure you understand it is not the distance from the trough to the crest. That's double the amplitude. The amplitude is the distance from the 0 resting position to the crest or from the zero to the trough. And guess what? That's the same distance because they move just as far up as they move down. The last one is called a node, and it's represented by this dot here. The node is simply the point at which the wave crosses that zero resting position where it used to be before the wave came through. So that's a transverse wave. You need to know those parts of a transverse wave. But let's go ahead and move on to the next type of wave, which is a compression wave. In a compression wave, the particles actually move parallel to the direction of wave propagation. Compression waves are also called longitudinal waves. You might need to know that term. But here's an illustration of what a compression wave looks like. Notice these red particles that have been highlighted in the illustration are simply moving back and forth. They go right, they go left, they go right, they go left. But if you zoom out a little bit and look at the picture as a whole, you can clearly see that there is a wave moving from the left side of your screen to the right side of your screen, but it's not carrying the particles. These particles are staying where they are. The particles are not moving left to right, but the wave is. Notice the wave is moving in the same direction as the particle oscillation. Wave is going left to right, particles move left to right. They don't move up and down. So that's called a compression wave or a longitudinal wave. Lots of different examples of compression waves. The most important one you need to know is sound. And if you look at this illustration really closely, you'll see some sound waves being emitted from this person's hands as they clap. They go really fast this way. Watch closely. There they go. They just move off in this direction really quick. It's not the air molecules, that's just disturbed air. The sound waves are going boom, boom. They just move that way. Here's another illustration of what sound looks like when you have a speaker moving. Again, notice the molecules are simply going back and forth, and the wave itself is radiating out in all directions. Energy spreads out from that speaker. Another example of a compression wave is a slinky. Now, a slinky can make transverse waves as well, but this is an example of how you can make a compression wave with a slinky. Notice all we have to do is compress the beginning part of the slinky, and that compression simply travels down the slinky in the form of a wave. Now, there's a really good example of this, a video that I'll post after this one. Tsunamis are also a great example, and some earthquakes, of compression waves. Last part of this video, I need to talk about the parts of a compression wave, just like we talked about the parts of a transverse wave, but this one is a little bit easier. So draw something like this in your notes. Pause the video if you need to as well. I know this is a little bit more difficult. Even if you just want to draw lines that represent what we're going to call compressions, that's fine as well. So parts of a compression wave, we have compressions. That's an area where the medium density is high, because what's happening is these particles come and they hit each other, and that's what transfers the energy. Well, where they hit each other, where they meet, the particles are more dense right there, which means if it's air, there's a lot of high pressure right there, and we'll get to that later. But high pressure area right there where the medium density is very high, and a rarefaction is an area where actually the medium density is very low, and that's these areas in between the compressions. And it's clear that you can clearly see that the particles are not as close together. That's why your eye can follow the wave across, because it sees the particles when they're closer together, when they're more dense. Last thing we need to know is the wavelength. We can also measure the wavelength in a compression wave as well, and it's, again, distance between successive parts of the wave. In this case, we usually measure the wavelength from compression to compression, from one compression to the next. You can also measure it from the middle of one rarefaction to the middle of the next one, but it's a little bit more difficult to do that. If you did, you'd get the same length like we did before with a transverse wave. So those are the types of ways, transverse and compression waves, but again, that's based on particle movement.